your or what is the level of strength you have achieved. So obviously it means that H18 will be much harder, meaning it will have a higher tensile strength as compared to your H11 series. So this is another to further get into detail. There are furthermore categories. Maybe it's not required for you to understand at least as of now. Okay. Similarly, your H2, as the name suggests, it is strain hardened followed by partial hardening. Many times it's required that these products are cold word more than required to achieve a desired mechanical strength. Okay, and sometimes it becomes difficult for subsequent operations. So you may have to go for a partial annealing, not complete annealing, but a partial anneal treatment to slightly soften it for subsequent applications. Okay, and also there are certain series of aluminum alloys, for example, aluminum magnesium series. Okay, this is nothing but your 3 series of or 5 series of aluminum alloys. So what can happen is in magnesium alloys generally after strain hardening, if you simply strain harden and keep it, it has been seen that your alloy gets softened over a period of time, okay, for due to many reasons. So for that series, generally what you do is you generally simply strain harden, meaning cold work it, and you need to stabilize it, meaning you need to anneal it for a sufficiently long time so that you can ensure or you can get a plateau in your property. That means you do not have, that means the hardness does not drop further on subsequent operations. Okay, so this H3 series generally it is applied only for your aluminum magnesium alloys, or not only binary combinations but also your ternary quaternary combinations as well. So this is something which is again very restricted. That means not all alloys are given this treatment. So this is a very common treatment, H1 and H2. So likewise H4 I told, so it's a very special kind of heat treatment where some partial annealing is done during a subsequent paint baking operation. That means or your painting operation or your lacquering operation. That means when you coat your or when you paint your automobile frame, that means the final coating is given. So this is the kind of treatment which is given for especially for your automotive sheets or any other sheets. Okay, again these are mostly applied to your those kind of products. So there are many more. So but these are the very important category of your H type of treatment. So again going back, if I go back, so these are different ways by which you strain harden and how you or how you stabilize your microstructure. So again depending also, so whenever you get any product, suppose you're ordering, you want to deal with a 2024 H1, you want to do some studies on this. So if they have the company has to indicate whether it is H1, H2, H3, H4, whatever is there. Generally H4 is very limited, but they have to clearly specify so that just mentioning the alloy will not do. Okay, whether it is F or O or H1, H2, H3, everything has to be designated. Okay, so this is what is followed by standard practice, which is so whenever you buy any product, you need to have the complete specification. Okay, so that is mandatory so that you have an idea of what is going on. So similarly for your cast aluminum alloys, you have a 3-digit nomenclature, something like this. Okay, you can say it is 1 XX.X. Okay, this is something, for example, for pure compositions, this is the kind of designation. Similarly for your, if it is a copper is the principal alloying element, this is the designation. Similarly for 3, your silicon is the principal alloying element, but in addition to that you also have your copper as well as magnesium, some amount of copper and as well as your magnesium. So likewise you can see for all the series, but here the nomenclature is slightly different. 8 here in this case, tin is the principal alloying element. Okay, in 8 series as far as cast alloys are considered, so tin is the principal alloying element. And likewise the 9 series is nothing but it is reserved for all other alloying elements. Like what was this is analogous to the 8 series which was for your wrought aluminum alloys. So here in this case your 3, 2, 3 and 7, okay, 2, 3 and 7 are the heat treatable alloys because 2 has copper, 3 has silicon, in addition it has copper and magnesium or both, Okay, that's why, and they can form precipitates. So that's why 3 also comes under your heat treatable series. Likewise, zinc, it can have elements like copper and magnesium. So that's why they are called as your heat treatable series. Whereas the remaining ones, 1, 4 and 1, 4, 5 and 8, so 6 is unused. Okay, still not much. Maybe we need to see the updated version of it, or what do you mean by this unused. But 6 is hardly used when it comes to just a minute. তখন আচ্ছা তাহলে ଅଲଗା କିଛି କମ୍ପ୍ୟୁଟରରେ ତାହେଲେ ଦେଖୁ ନହେଲେ ଆଉ କ'ଣ କରେ ସେଠି ବି ଶୋ କରୁନି ଓକେ ଓକେ ଠିକ୍ ଅଛି କଥା ହେଇଯାଉଛି ଜାଣ ହଁ 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 କ'ଣ ଦେଖୁନି ଆଚ୍ଛା ହ୍ୟାଲୋ ହଁ କୋଉଠି ସେ ତମେ କୋଉଠି ଲାଇବ୍ରେରୀରେ ଅଛ ଆଚ୍ଛା ତାହେଲେ କ'ଣ କରାଯିବ ତାହେଲେ କାହିଁକି ଶୋ କରୁନି ଏଇଟା ଉଁ, ଉଁ, ହଁ ଠିକ୍ ଅଛି ମୁଁ ଟିକେ କ୍ଲାସ୍ ପରେ କରିବି ତାହେଲେ ଠିକ୍ ଅଛି କ୍ଲାସ୍ ପରେ କରିବି Okay, so coming back to this, so this is how you can, or what does the designation mean? For example, say I have, say, this particular alloy, this particular cast aluminum alloy, 150.x. So what it simply means that, so you have a minimum of 99.50. Okay, so this is the purity of your aluminum. That means the remaining 0.5 is nothing but some kind of impurity. Okay, again, if you get into more details, for example, say if I have 150.50, it simply means that the 0 stands for your castings. Okay, that means aluminum castings which you have made. But if I put 150.1, say this 1 stands for your aluminum ingot. There are many more, 150.23. So all these, so that means you need to be very careful about whatever is written. You just should not take into consideration that these both of these are same. It only means that the composition is, its composition could be same, okay, but in different forms in which it is available. So that has to be understood very clearly. So likewise, anyways, it's not required in too much details, but but you need to understand that yes, these two are different forms of your this particular pure aluminum alloy, so which is about 99.5% purity. Okay, but this does not have carry any meaning when you talk about the other series. Okay, so in 2XX to 9 series, the second two digits have no meaning. That means if it is 250.x, so it does not mean that it is 99.5. It does not have any meaning in fact. Okay, only for one series this kind of designation holds, like we have seen in your wrought aluminum alloys. Like some of the important, so you can see if we see this particular alloy, so immediately what should come to your mind, for example 201.0. So immediately if you see such type of designations, so you should understand that we are talking about a cast aluminum alloy. Okay, just for to highlight one such alloy, this is a very important aluminum alloy. In fact, it's one of the most widely used aluminum alloy. Okay, at least cast aluminum alloy. Okay, these alloys, it's especially your automotive industries, all those cylinder heads and many powertrain, those components are all made using this A356 alloy. So again, these are the typical designations we have seen, like in the wrought aluminum alloys. So these are the limits which have to be followed for different elements to be called this as a A356 alloy. You can see it has it's a hypoeutectic aluminum silicon alloy. If you remember the phase diagram, so where the eutectic is at 12.6, so this is clearly a hypoeutectic aluminum silicon alloy, but with other elements like your copper. Then you have a little bit of, say you can have a little bit of manganese, then magnesium and zinc and titanium. These are the other alignments which can be tolerated to this particular extent. Okay, so this is how you can see so many series of aluminum alloys. You can see, of course, depending on the application, you need to synthesize different kinds of, for example, 8 series. It contains a large amount of your tin. Okay, this is as I told, 8 series is nothing but your aluminum tin alloys. Similarly, for your heat treatment, we have different kinds of designation. So we'll be reading about this in detail again when we talk about your the heat treatment, the processing using your heat treatment. But for the time being, you should know this definition. So if you see, the ones highlighted in green. Okay, so green, you can see these all are your naturally aged condition, meaning suppose you have a T1 sample. Okay, meaning suppose you have a say a 2024 alloy followed by T1, if it's written T1. So what it means that the alloy must have been cooled from some elevated temperature, say some casting process or some shaping process, and then naturally aged to a substantially stable condition. So that is what we mean by this T1 condition. Now the same alloy, if you cool it from an elevated temperature, then you slightly cold work it and then naturally age, then that will be called as your T2 treatment. So likewise, all these terms, all these nomenclatures have a meaning, and that is the reason why you do go for all these heat treatment for different alloys. Okay, to achieve your specific properties. For example, sometimes you may go for heat treatment so that the alloy becomes more can be easily cold worked. Sometimes you go for heat treatment so that the alloy can be hot worked very easily. Okay, sometimes you go for a specific heat treatment where your strength is the only consideration. Okay, and sometimes you go for a treatment where you want a slightly higher ductility in your sample. So all of these can be achieved. Okay, that means the combination of properties can be achieved only when you follow these different types of heat treatment. So broadly speaking, these are the 10 different types of heat treatment which is generally carried out and designate. There could be some variations of all these, but these are the broad categories of your heat treatment. The ones highlighted in green, it pertains to your naturally aged condition, whereas the one written in this blue, it belongs to your artificially aged condition. So if you have read about your precipitation hardening, if you remember the when you read about your how this precipitation hardening alloy works or what's the mechanism, you must have gone through your naturally, what you should know what is a naturally aging treatment, what is a artificially aging treatment. Okay, so we'll talk about this in details maybe when we discuss your heat treatment or processing using heat treatment. Just to give you one example, say 6063 alloy. So this is a wrought aluminum magnesium silicon alloy where you have magnesium as well as silicon, because this is 6, right? So now if you see this property of this alloy, how it varies as a function of different tempering conditions. Okay, not only tempering conditions, say you give some heat treatment, some hardening, cold, we have just now seen some cold hardening operation even in the H18 condition, meaning the full hard condition. So if you heat, so if you in the full hard condition, you can see the strength you can reach for this 6063 is around 150, and the tensile strength which you attain is your 200. Now the alloy in the annealed condition, you can see this is the annealed condition where you have your 50 as your yield strength, 90 is your tensile strength, and your elongation is 30%. That means as you cold work this alloy, so you can see there is a huge drop in your ductility from 30 to 8. Okay, the same alloy, if you from your annealing condition, if you the same alloy, if you do a full hard treatment, you will get a drop in your ductility, but what you get is it almost more than 2 times increase in your tensile strength. So that means whenever you have such a table, so you should be able to read this information. So what do you mean by this? So all this has to be very clear to you. For example, just to show you one example, T4. So T4 is a naturally aging condition, okay, where the alloy is naturally aged. So you can see these are the properties, that is around 90 90 megapascal yield strength, 170 is your tensile strength, and 22% elongation. With the same alloy, now if you go for artificial aging, which is the T6, okay, you can see the strength, okay, the strength increases to around 215. That means in T4 it is 90, in T6 it is 215. Similarly, your yield ultimate tensile strength also increases from 170 to 240. But what you're compromising is you're compromising or sacrificing the ductility. So why does this happen? So you need to understand all of this because it has to do with your precipitate volume fraction and other quantities. Okay, so all of these have play a very important role. So it's obvious that so one heat treatment is leading to the different. So that means all the heat treatment is leading to different properties. So obviously your microstructure or the amount of precipitates is varying significantly. That's why it's showing up in the difference of all these properties. Okay, so you need to read about maybe how are these precipitates formed and other details. That means you need to revisit your precipitation hardening chapter. Okay, from the, maybe you can follow your Abner or even it is there in your Callister. So please get into the details or the basics of all these phenomena again. So the bottom line is here in summary. So all these tempered conditions are known to you. So you should be able to read and understand this particular property. That means the same alloy you can see, you can generate this entire spectrum of properties. That means you can have a variation in your tensile properties, variation in your elongation or ductility, because all of these are going to decide for which application or which treatment you are going to follow. Okay, so that's why you can see you can play with your properties of this particular alloy just by playing with your different cold working operations. Not only that, you can also by following different temper, that means by different kinds of heat treatment, so which will result in your different properties. Okay, so you need to be aware of, or you should be able to interpret all these data and the information which is given to you, and choose the right temper condition for a particular alloy, because all this data is available, okay, in the literature or in certain ASTM in some ASM handbooks. You have this data available for at least some of the popular aluminum alloys. So you should be able to pick the right kind of treatment for your alloy. I'm not getting to all these things. Since we are talking about cast aluminum alloys, right? So there are different aspects. So you must have read it already in your undergraduate studies. So what do you mean by castability? So castability, again, it is a it is sum of several factors. Okay, that means castability is not just to do with that your so fluidity is so many students they get confused that castability and fluidity are same. No, it's not the same, because fluidity is something to do with the flow of your liquid metal only. That's what we are interested in. But when you talk about castability, it includes many other aspects. That means whether it's fluidity, how easily your liquid metal is able to fill the mold, then there are volume shrinkage related issues, then whether the alloy is susceptible to hot tearing, or we call it hot susceptibility to hot tearing. Okay, so that's another important. And whether the alloy, if you choose if the alloy composition is not right, you may also end up getting your porosity in your castings. Okay, and your surface quality, that means the surface quality also comes under your castability. So that means you need to choose your alloy or your and the entire parameters related to your casting. So all the parameters which are related to the casting are will come under your castability. So it's not the same fluidity and castability. When I tell an alloy has good fluidity, it does not mean that it has good castability. Okay, so castability should satisfy all of these conditions. When I tell it's a good castable alloy, so that means it has to satisfy all these conditions. Okay, all of these conditions have to be satisfied. So we will go through some of these in very brief. For example, fluidity. Okay, so whenever we talk about a good castable alloy, the most important parameter is your fluidity. That means it has to be really fluid, meaning it has to have very lower viscosity at the temperature of pouring. So when you are going to pour, so you need to ensure that the alloy has very fluidity even at the pouring temperature, because you know that the pouring temperature always generally is slightly in most of the cases lesser than the superheat than the actual processing temperature. So the fluidity is reduced as the purity of aluminum decreases, okay, and the alloying elements are added. Then what's the reason? Because there are several reasons for it, depending on which alloying element we are talking about. Generally, it is seen that if you have a very wide freezing range alloy, okay, so that means, for example, if you are having this alloy, it has a very wide freezing range, right? Versus if you are very close to the eutectic, which has eutectic has zero freezing range, but if you are close to the eutectic, the freezing range is very less. So the freezing range can also dictate your mold filling ability or the fluidity, because when you are having a wide freezing range alloy, you are passing through this liquid plus your solid zone, and if that solid phase, if it hinders the movement of your fluid, or it hinders or it affects the movement of fluids overallly, that means on a macroscopic scale through the mold, or it can also affect the movement of your fluid when your dendrites are forming. Okay, so there are other aspects which can affect the fluidity of your casting. Similarly, if you have an alloying element which forms a large number of intermetallics, and that too if the morphology is not suitable, so that can also interfere with the flow of your liquid. And again, we'll be reading about this when we read about solidification processing. Your front, that means how your solidification proceeds. Okay, there are different kinds of solidification modes we'll be reading later on, so that also decides whether your mold filling will be easy or difficult. So just to understand this diagram, so this is that let us say a typical eutectic phase diagram, right? So what is shown here is that how your fluidity changes with your alloy composition. For example, for three alloys are shown here. So this is one alloy, okay, it's a hypoeutectic alloy, and this is the eutectic alloy. Let us say that this is a hypereutectic alloy. You can see these points. So this is a fluidity distance. So it shows that this alloy has whatever is the fluidity distance, okay, and this alloy has very high fluidity. So and this alloy again has low fluidity. Okay, so what it shows that the eutectic composition has the best fluidity. Okay, it has in fact it has the highest fluidity amongst all the compositions. Now the reason for this is because you have a very high, because this particular composition has 100% eutectic, right? It is 100 because this is a eutectic composition, and it is the lowest melting phase. So lowest melting eutectic mixture. So that's why you can expect it to have a that means in any alloy, okay, in any alloy, if you have higher volume fraction or weight fraction of your eutectic phase, so you can expect that alloy to have a better and better fluidity. Meaning, if you deviate away, that means if you are away from this eutectic point, either on the hypo side or on the hyper side, your fluidity is going to vary because your fraction of eutectic is varying. So generally, as far as your cast alloys are considered, so the best amongst all the alloys, okay, that means if the three series alloy has the best castability. So this is in the decreasing order of castability. So 3, 4, 5, 2, and 7. Okay, so this is the order of your castability of, that means what it means that the three series of aluminum alloys are easy to cast as compared to 4, 4 is easy to cast as compared to 5, and so on. And there the answer lies in many factors like your formation, whether it's possible that this series forms a lots of intermetallic compounds, okay, and other things as well. It could also depend on the freezing range as well. So how do we measure this fluidity? Okay, yes, this is what I was talking about. For example, when you're freezing any alloy, so assume a liquid is fluid, you have cast a liquid metal. Okay, it's not only the flowability which is important. So it's also, you can see when you're freezing any alloy. Okay, and let us assume that this is a one kind of directional solidification. You'll have some dendrites forming, right? So this shape of these dendrites, the manner in which these dendrites grow, then suppose they are forming some intermetallics. Okay, so it's the morphology of this intermetallics. So that will also play a role whether the liquid is able to flow very easily. Okay, so that's why you can see it's not only the liquid of temperature, the other factors which can hinder the movement of your liquid, and that also comes under your fluidity. So all these factors can affect the fluidity of your melt. It's another aspect is the ability to feed the interdendritic spaces. Interdendritic spaces is nothing but the spaces within your dendrites. Though it's a schematic diagram, so I'll show it to you. So the interdendritic, how this liquid is going to pass or flow through this particular dendrites, because remember this is not only, it's not these dendrites are simultaneously growing as well, right? It's also simultaneously growing in size. So that means as it grows, so you'll have more hindrance for the flow of this liquid metal. So these also affect the fluidity of your casting. So those also, so these factors also have to be taken into consideration. And as the liquid is dropping, obviously the melt viscosity is changing, all your surface tension forces are going to change. So many factors coming into picture when we talk about your fluidity or your castability of your melt. It applies for any kind of alloys we are talking about. So how do we measure this fluidity? So that because we have to quantify, right? So some of the ways, if you are in the undergraduate, you must have read. So this is a very common test which you see. We call this as the spiral test. So what you do is you have a liquid metal, you pour it through this particular pouring cup or sprue, okay, and it fills this particular mold. So it's a spiral mold, okay. So a known amount of liquid molten metal at a particular temperature is poured, and you can measure. Suppose you want to compare, say, a 2 series versus a 3 series of aluminum alloy. You can do that. So some certain parameters have to be kept fixed. So the distance it is flowing, okay, through this particular spiral, so that is the measure of your fluidity, or that is simply called as your fluidity index. It's nothing but you are measuring this particular distance that alloying element is flowing. Suppose there is another alloy which has which is almost flowing till this particular distance. So obviously you can tell that the alloy has a higher fluidity than this particular alloy. The other way of or some latest ways by which you measure your fluidity is vacuum test, we call it. So what you do is you have a tube, okay, which is kept inside or inserted inside this liquid metal, and you apply a known vacuum, okay, in standard a known vacuum. So you drag your liquid sample and you measure what is the fluidity length, okay, and that is another way by which you measure the fluidity. Again, here you see this is the distance which is traveled by this particular liquid. So of late, there is another way by which people are measuring your fluidity. You can see this is the arrangement. You can see 1, 2, 3, 4, 5. There are 5 fingers, we call it. Okay, so here you have the liquid metal which is coming from the top, and it will flow along this particular channels. Okay, and you can so in this test what you do is you need to measure the length of this particular liquid, okay, the length of the solidified casting. So that will give you an amount of what is this. So higher the number, the higher is the fluidity. So the common thing in all of this is nothing but you are measuring the length of the solidified metal. So fluidity index is nothing but the length of the solidified metal in the spiral passage, or in this tube, or in this particular mold, whatever you can call it. Okay, so depending, there are several more tests, but these are some of the tests which are available in the literature. Okay, so greater is the length, the greater is the fluidity index. So this is how foundries quantify the fluidity of your different cast metals. The other aspect, as I told, your volume shrinkage. Your volume shrinkage again depends on several factors. Okay, several factors associated with your depending on the alloying element which you are adding. You have a range of aluminum alloys, right? So all aluminum alloys or any alloy for that matter, if it will follow this particular path from a liquid, it enters into a semi-solid zone, that is your liquid plus solid zone, and then finally it solidifies, right? So since you're passing through all these zones, so the three stages will be liquid shrinkage. This is something which we are not too much bothered, but what we are bothered is how the shrinkage takes place in this particular zone, because that's the most important thing. Because after here, after this, it does not matter too much. So we need to understand how the shrinkage takes place in this semi-solid zone. Okay, so these are the several stages at which, or as the temperature is dropping, how your volume shrinkage of all these aluminum alloys takes place. Again, as I told, it will depend on the alloying element which is present. For example, let us say a case of a eutectic aluminum silicon alloy. It shows only 4% shrinkage, but if you go for hypereutectic, it shows further lower shrinkage. But pure aluminum, on the other hand, if you can see, it shrinks by around 6 to 7 volume percent, where the shrinkage is very, very high. For aluminum, generally, it has a very higher shrinkage as compared to your iron or cast iron or those kind of metals. Okay, so that means you need to your calculations have to be pretty much accurate. Okay, so when you deal with all these volume shrinkage calculation, you need to choose your molds properly. You need to design your casting molds also appropriately, so that it can compensate for all those shrinkage. So as I told, the shrinkage, so it's nothing but an overall contraction. So it can also lead to, it can be seen as a localized effect at certain surfaces. You can see the shrinkage. Then there could be some internal defects as well, where like your isolated voids or interconnected porosity. So this could be the result of your shrinkage of your several aluminum alloys. So what are the factors which affect? There are many factors, though I have listed only 3 of those. So alloy composition, your mold design, then how fast you're cooling your mold, and finally your mode of solidification. Though we are not, you're not aware of this, so we'll be seeing about this later on. Okay, so there are different solidification modes for different pure metals as well as for different alloys. There's another concept of your hot tearing. So whenever we talk about your cast metals, okay, so many castings, it is you see that you'll see some surface cracks or cracks at certain junctions of your castings. So if you don't design a mold properly, so that could be one. Sometimes it's the basic characteristic of the alloy composition. That means you need to modify your alloy compositions, or you need to tailor your composition accordingly, so that you don't get these cracks. So why does this crack occur in the first place? So these cracks occur because, or when, the tensile stresses generated within the solidifying casting exceeds the fracture stress of the partially solidified metal. So this is one theory. Okay, this is one theory which tells that why these particular cracks are generally visible in many castings, again at certain locations only. And this particular phenomena is called as the hot tearing, because it occurs during the solidification process in the hot condition itself. It's not anything after that. Okay, and it's due to this. This is one of the reasons by which your hot tears appear in your castings, and mostly these are surface cracks, which you can see it. If it is a very fine crack, you can use your some certain NDT techniques. Okay, otherwise most of these cracks, if the very macroscopic crack, you should be able to see with your naked eyes itself. Okay, and these cracks, all these hot tears are very common in your 2 series and your that means aluminum copper alloys and aluminum magnesium series of series. You hardly see this in your aluminum silicon alloys. Okay, so this is so certain, that means it also is a function of, so that means how do we make then these aluminum copper alloys? So if you end up always getting hot tearing, no, you can tailor your composition in such a way, okay, and you need to design your molds in such a way so that you can avoid this particular. It's not always it's mostly a system specific problem, meaning which system we are talking about. Obviously, it can sometimes occur due to a faulty mold design, but that can always be corrected. But you need to be sure about this particular condition. That means the mold, alloy composition also has to be chosen appropriately so that you don't end up having all these defects. Like this is how it will show up. If you go into the details of the microstructure, you can see this particular intergranular cracks which is occurring, so which will appear as hot cracks on your surface. Like if you see, you can see this component has cracked. It's completely cracked. So this could be either due to your faulty design, but you can see it's all over the sample at all the locations, at identical locations, right? So this could be one, could be due to your poor design of the mold itself, or it could be due to your an improper alloy composition. You can see hot cracks everywhere. And this is a very serious problem in many aluminum castings. Okay, many aluminum castings. Still, the foundries report this, because the understanding behind this was quite less, and not many techniques were there to see how this cracking is occurring during the solidification. It's sometimes very difficult when anything is happening in the liquid or in the semi-solid state, right? So it becomes difficult for the science to understand. But with more modern equipment, so now we understand the reasons for your hot tearing in different kinds of alloys, and more or less the issue has been solved, at least in case of a lot of studies are going on even in the aluminum copper alloys till now. Okay, so to understand, so what can be done to overcome this hot tearing issue, because once you get a hot tearing, the alloy is simply reject, that component is simply rejected, right? It's of no use. So maybe next class we'll read about another the most important class of your cast aluminum alloys, that is your aluminum silicon alloys. This is, we have maybe only few slides which will talk about this, and so that will be it for your processing of your aluminum alloys. Okay, so read. So I think the ASM handbook I have sent, you go through it. Okay, read the relevant portions, and I will send you maybe once again all the contents that have been covered in the class. Okay, so go through this if you have recorded. So go through this video lectures. Okay, you will understand many of these things, but still you need to go through other sources as well. Okay, so you need to understand, relate the so many aspects of all this processing of your aluminum alloys. So the wrought versus your cast. Yeah, any doubts, students? So I'm trying to go pretty fast because a lot more things are to be covered. Okay, if you have any doubts, you can drop me a mail. Okay, I think if you have started reading only, you will have doubts. Else you will not have any doubts. Yeah, Aryabhatta, anything? Any doubts? Aryabhatta? Okay, if you don't have any doubts, maybe we can meet on Tuesday. Okay?
Yes, sir.
Yeah.
Yes, sir.